All right. Well, today we're going to develop the Fourier series expansion. That is, we're going to learn how to write any function as a series of sine and cosine functions, okay? Which is going to be really useful. Let's see how that works, all right? All right. So any function, well, often it's useful to expand a function as a series in terms of some simpler function. For example, we know that we can write any function as a polynomial series. For example, we've learned that the function e to the exponential function, e to the ax, can be written as a series, a polynomial series, 1 plus ax plus 1 over 2 factorial times ax squared plus 1 over 3 factorial ax cubed, and so on. In fact, we developed this very series by using a Taylor expansion early in our class, okay? The reason we can do this is that the polynomials form what's called a complete set. That is, any function can be expressed in terms of a polynomial, like this one. For some cases, that might be very useful. For other cases, the original function might be more convenient. But having this series expansion gives us a lot of options, okay? Today, we're interested in the Fourier expansion, or the Fourier series expansion. In the Fourier expansion, we expand our function in terms of sine and cosine functions, okay? Now, we'll define this in a moment, but to begin with, let's consider a function that's periodic, or it's defined over a limited range of x, okay? Here, let me sketch an example of a periodic function. So I'm just trying to draw something that's periodic, but it's not a sine or cosine function. So maybe it looks like this. Well, I'm not doing such a great job, but maybe you get the idea. I'm trying to draw a function that repeats with a period. We'll call the period L. So we might call this point here x equals 0. And if we do, then one cycle over, we have x equals L. And the next cycle over, we have x equals 2L. And the function continues both to the left and the right. So that's a periodic function, okay? Alternately, we could be talking about a function that's only defined between x equals 0 and x equals L. So a function defined over a limited range. In that case, we're going to work with it by assuming that by treating it as if it's periodic with period L, okay? Okay, and we're going to assert that we can represent this as a series in terms of a series of sine and cosine functions. And why do we expect this? Well, sine and cosine themselves are periodic functions. And so it seems like if we add them together, we should be able to build up a more complicated periodic function. Okay? In fact, formally, sine and cosine form a complete set. That is, by adding together sine and cosine waves of various different frequencies, we can build up any function that's defined over some range of x. All right? So it's that mathematical fact that guarantees that this will work. And now let's look at the technique we can use to do this. Here, 1 second. So what we're going to assert is that any function f of x can be expanded as a series of sine and cosine functions. Here, I'll write down the series. Oops, I didn't leave myself enough room here. I'm just going to move this over a little bit. All I need to let you know is that this series continues. So it's equal to a constant plus a series of cosine terms plus a series of sine terms. Okay, I can write this more compactly using summation notation. What I'm saying is that f of x can be written as a constant term plus the sum over n equals 1 to infinity of a coefficient, a sub n, times the cosine of n times 2 pi over L times x, plus the sum, n equals 1 to infinity, of terms b sub n times sine of n times 2 pi over L times x. Okay, perfect. Here, let me just draw a box around this. So I've just asserted this so far. I haven't proved it. I haven't proved anything. Okay. But let's look at this expansion for a second. All right. Notice that we have cosine and sine functions. We have a whole series of them, but we don't have any possible frequency or wavelength of cosine and sine function. Instead, the thing in the argument is always n, an integer, times 2 pi over L times x. And let's see why that is. Well, we're trying to build up a function that has that's periodic with period L. And in order to do that, we can only build it out of sine and cosine functions that are themselves periodic with the same period. Okay? Suppose n is equal to 1. Then we would have a cosine function here, which repeats in the following way. When x is equal to 0, we have some value. Well, the cosine function would be 1. As x gets larger and larger, that would change. But when x was equal to L, then the argument of the cosine would be 2 pi. And that means we would have gone through one entire cycle of the cosine function. We'd be back to the beginning. In other words, the function would repeat. That's what happens for n equals 1. For n equals 2, well, we get 2 cycles between 0 and L. For n equals 3, we'd get 3 cycles. Well, you can see how this works. Any one of these, or any term in the series that I've drawn here, will repeat either once or multiple times in the range 0 to L. So anything we build out of this will also be periodic with period L. Maybe with a shorter period too, but in general, periodic with period L. The same thing is true for the sine terms. Okay? Oops. Didn't draw that last one quite right. Oh, in fact, I didn't draw any of those right. Sorry. 1 cycle, 2 cycles. Okay, 3 cycles. All right. So we're building up our function out of sine and cosine functions. Because our function is periodic with period L, we can't just use any arbitrary frequency for our sine and cosine functions. They have to be set up in this way, where the argument of our cosine or sine function is an integer times 2 pi over L times x. That way, when x changes by an amount equal to L, we'll go through an integer number of cycles of each of the waves. Okay, but this will work. And we know this will work because it can be shown mathematically that this set of functions that we've drawn here are in fact a complete set for functions, for a periodic function with a period of L. Okay? Now, it's useful to write this down, but of course this is totally useless until we know what the coefficients are. That is, until we know what each of these, A0, all of AN for any value of N, BN for any value of B. We have to know the expansion coefficients to be able to use this in any particular case. All right, well, that's what we'll take a look at in the next video.